In this video, we're going to look at Thomson's plum pudding model, sometimes also referred to as the Raisin Bun model, but yeah, that's kind of an American thing. And to be able to do this, we do have to start talking about some other stuff, a little bit of stuff first. And I promise you, though, eventually we will get to Thomson's plum pudding model, and more importantly, the experiment he does that leads up to him getting the idea for the plum pudding model. So the first thing we're going to talk about is actually John Dalton. And if you do think back to models of the atom that you're supposed to know about, John Dalton kind of gets the credit as having the original first model of the atom, sometimes called the solid sphere model, also sometimes referred to as the billiard ball model. And I know billiards isn't as popular a game, but it's basically like pool. So imagine something like a pool ball, a very solid sphere that you can't like break into pieces or something like that. Now that's exactly what John Dalton is trying to explain, because he's coming at this from a chemistry standpoint. He's looking at a periodic table of the elements where he's basically saying, hey, every atom is its own distinct thing. And in his view of atoms, the atoms are indivisible. So if you have a single atom of sodium, it is a ball and it's solid. You can't break it up at all. And if you have a solid sphere atom of gold, it's again a solid ball that you can't break apart. And in his view of things, sodium atoms are smaller, so they would be physically a smaller ball, and the gold atoms would be bigger, and they would even have physical characteristics like it would look gold, like it would be shiny yellow metal colored and stuff. This was his way of kind of thinking of how physical characteristics were manifested right down to the level of the atoms themselves. Now, the strength for him here is he's looking at this from a very chemistry, early 1800s kind of way of thinking of things, of how atoms combine, and that you can't create or destroy these atoms. It's like you're writing out a chemical reaction and you have to balance it. You start with a certain number of sodiums, you end with a certain number of sodiums, and the solid sphere model lets him do that. The weakness, though, is how does this explain chemical bonding? Because when you think about like pool balls on a pool table, you don't exactly think of them grabbing hold of each other. Quite the opposite. They'll bounce off of each other and stay separate. So with no knowledge of things like positive and negative charges in an atom, because to him these are indivisible, he doesn't have any idea of explaining chemical bonding. So he kind of stalls out there with his model. But it's a beginning point, and we are talking about atoms as being discrete units. So that's good. Okay, he's got something going there. Now, again, before we get to J.J. Thomson and his stuff, we do have to talk a little bit about cathode ray tubes. And I'm going to start this round while I'm talking about stuff, just so you can kind of keep a bit of an eye on that. So cathode ray tubes were this idea of building a tube, a vacuum tube, and putting essentially plates at either end. And one of them is going to be negative and one of them is going to be positive. And you just zap them with a really high voltage. And if you do this, and I think in this video here he zooms in a second, if you do this, you can see a faint glow like that going across the tube. And they were able to show that these rays were coming off of the negative onto the positive plate. Now today, we can think about that and say, what would move on its own away from negative and towards positive? That'd be electrons. Now they're not there yet. They're not thinking in the sense of little subatomic particles like that. But they are playing around with these cathode ray tubes. And they're calling them cathode rays because of the mysterious rays going across, with anodes and cathodes, negatives and positives. And you can see he's bringing a magnet nearby now, and you can deflect the path of these mysterious cathode rays as they go through here. In this time period, there is this guy that I mentioned here named William Crookes, and he's making like the best cathode ray tubes that anybody has ever seen for doing experiments and stuff, to the point where they're actually referring to them as Crookes tubes. And everybody's fooling around with them, but nobody's exactly sure what they're seeing, what they're dealing with. And that's where J.J. Thomson comes in. J.J. Thomson starts playing around with cathode rays himself. And he's got these tubes and he's shooting things around, and he starts trying to do experiments. And he kind of famously does three things. The first two, to be quite honest, aren't as important to us because he doesn't really get conclusive information or results out of it. But it's what leads to the third one. So the first thing he does is he tries to use magnets to separate the negative charges out of the cathode rays. Well, you just saw that guy in the video using a magnet to bend the path of the cathode rays. But what J.J. Thomson is missing, or at least first missing, is the cathode rays are the negative charges. The cathode rays are electrons. So trying to separate electrons from electrons, well, you're not going to be able to do it. So he starts realizing that the negative charges are these cathode rays. Next thing he tries to do, he says, so they're negative charges. Let's try using an electric field. Let's try to deflect them. So think about the questions that we did way back when we were doing like parallel plates, and we would say that you were shooting charges in and that we could deflect them. So they would do like parabolic paths and stuff. He does that, and he's like, wow, look, it's doing exactly what I would expect them to do. Look at these crazy little charges changing their path, doing parabolic motion, projectile kind of motion, as they go through these electric fields. What's he going to do next? He decides to do both at the same time. He says, what if I use magnetic fields and electric fields at the same time on these charges moving through these cathode rays, or cathode ray tubes? So he builds something. Now, this is the very first part of the diagram that you're seeing up in the, this way, up in the top corner over there. So imagine something that would actually look like an Erlenmeyer flask sideways, and it's flaring out over here. This is just the first part, sort of the neck of the Erlenmeyer flask. And he's got a wire filament that he's stuck in there, and honestly, he just heats it up. Like if you just run electricity through a wire filament, as it gets hot, ping, 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 ping. It's a metal. It loses some of its negative charges, its electrons. That's why the metals form positive ions. So ping, 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 all these little negative charges, negative electrons are coming off. Some of those negative electrons, which really in terms of the kinds of speeds we deal with, they're not moving very fast, but they come off of that wire filament, and you can see randomly some of them go through these parallel plates because we've drilled little holes going through it. So just randomly, some electrons go through those parallel plates, and you notice we've set these up with the negative on the left and the positive on the right, so that negatively charged particles, the electrons, will speed up as they go through those plates. They come out the other side, and we know that they're going pretty wicked fast now, and that's when they enter parallel plates that are like this. Now, this is going to be very much like the classic sort of projectile motion kind of stuff that we did a few chapters back. As the electrons enter into there, in this particular diagram, they're going to want to curve upwards because they want to get closer to the positive plate and away from the negative plate. So that's just how the electric field is affecting them. They'll curve upwards. At the same time, though, that we have this electric field, he uses coils of wire with current going through them to make electromagnets. And in this particular diagram, what I'm telling you is we want to set it up so that the charges that are being forced upwards that way by the electric field, we want to get them to be forced downwards by the magnetic field. So take a second and just kind of see if you can figure out, using hand rules, what direction the magnetic field would be pointing in that sort of neck of the Erlenmeyer flask right there, where the magnetic field will point so that there's a magnetic force pointing down. So as you're doing the hand rule for this one, I'm hoping what you're getting is that your fingers have to be pointing into the screen, because with the electron traveling to the right, we need to have a magnetic field that points into the screen, and that's going to be what causes a force downwards. So you can see for the path given because of the electric field, I'm showing it curving up in blue, and the magnetic field is going to push it down. Now, this is where J.J. Thomson had to tinker with this a bit. He had to get it just right. So as much as the electric field was causing a force pushing up, the magnetic field caused a force pushing down. And if he tinkered with this just right, he could get the electron to go straight through. Now, on the far side of this diagram then, this is why I said it kind of looks like an Erlenmeyer flask, because it flares out on the other side. If he has just the electric field on, the path goes up. If he has just the magnetic on, it goes down. And if he has both on, it goes straight through. And the way that he can see that is that on the far side of that kind of Erlenmeyer flask, on the roundish part, he had this phosphorescent powder that when it gets hit by electrons, it glows. So he could see when just the electric field was on, there was a glow up at the top. And when just the magnetic field was on, there was a glow at the bottom. And when he had both on, tinkered just right, it would go straight through and he would get a glow in the middle. Now you might be saying, why is he doing all this stuff? Because he could calculate the speed of the electrons and da-da. Oh no, he couldn't. Because remember, we're still kind of like before anybody's talking about this being actual electrons. Nobody knows the charges or the mass of these little critters. So he's doing all of this without the ability you have of using like kinetic energy formula, EK equals 1/2 mv squared, along with the voltage formula, V equals delta E over Q. He can't do any of that stuff. He doesn't have the mass or the charge to stick into those formulas. So he comes up with something more elegant. And it's because of this getting them to go through, straight through path, that the electric field and the magnetic field must be exerting equal forces in opposite directions so that the net force is zero. So what he does is he comes up with something called the velocity selector formula. In this formula, what he basically says is exactly what I was just saying. We have the electric field force that was pushing up, and we're going to exactly balance it with the magnetic force pushing down. So we have these two formulas, Fe equals EQ and Fm equals QVB. Those two forces are equal in magnitude but opposite in direction. So we're just going to basically say they're equal to each other magnitude-wise, and we'll substitute in stuff on both sides. EQ equals QVB. Now check it out. We get to cancel Q, which is good because J.J. Thomson doesn't know the charge of these mysterious little negative things that are flying around in his cathode ray tubes. So we cancel that out and we get this formula that we can manipulate, solve for V. And sorry, I've got sort of this thing in the way here. I'll try to move it out of the way for you. Oh, take it back. So what he's got is this formula now, V equals electric field over magnetic field. He can measure both of those things. Those are both measurable things because he's making the electric field between those plates, and because he's using coils, basically setting up an electromagnet, he can measure that magnetic field. He's got everything on the right-hand side. He can measure the velocity of his particles, these mysterious little negative charges, without knowing anything about the little negative charges themselves. Now, I don't often say this, but this is a formula that if you're not going to remember all these steps for putting it together, memorize it. Because going off way into the future for like a diploma exam or something, this is a formula probably you're going to use. So I used to just always remember it as VEB, V-E-B, V equals E over B. And then I'm good to go if I'm doing anything with a J.J. Thomson type experiment. So right here, that's what I'm telling you. I'm doing a setup like J.J. Thomson's, which means all the fixins are there. The electric field and the magnetic field, everything's there. And that what I've got is that perfect balance where I've adjusted my electric and magnetic fields so that the particles are going just straight through. So I'm going to take my formula and I'm going to fill in stuff on the top and the bottom. And all I need is the electric field and the magnetic field. That's it. So I just stick those numbers right in and I do the math on them. And I find out that in this particular setup, the only way for this to happen, to get those two forces exactly balanced, is if the electrons, the negative charges, are moving at 2.09 times 10 to the 7 meters per second. Great, I've got the velocity. Now what can I do with that? Well, that's what J.J. Thomson is asking himself. What can I do with that? So what he does is he comes up with a way to kind of do a different stunt with this setup. He turns off the electric field. Now he's got just the magnetic field going. And do you remember when we have just magnetic fields with charges shooting into them perpendicularly? We can capture the charges. If we have enough magnetic field, we can get them to go in a circle, right? Well, J.J. Thomson's experiment, the way he's got it set up, it just has them curve downwards and then they come out the other side and finish off and hit the glass. But he can extrapolate what the radius of their path would have been if he had a big enough magnetic field covering enough like area of space that he would actually get the negative particles caught. So he extrapolates what that radius would be, and he says, oh, so if I'm doing that, and this goes back to the stuff that we did a chapter ago, basically a couple chapters ago, where we would capture charges in magnetic fields, the magnetic force is the centripetal force. QVB equals probably mv squared over r. That's the most common centripetal force formula we're going to use. In this, I can cancel one v on both sides, and then I can manipulate it to solve for q over m. Now that looks weird because we don't usually solve for two things on one side. But you do have to remember for J.J. Thomson, he doesn't know the charge or the mass. So he solves for q over m, and he's got the other stuff that's on the other side, but he calls it the charge to mass ratio, because that's what it is, q over m. Q as a ratio with m. And he basically says, I wonder what sort of number I'll get. So here's a big question for you. Look at all those numbers and everything. So it basically tells you, yeah, we set up a cathode ray tube experiment like J.J. Thomson's. We had the electric field and the magnetic field turned on. When we did that, electrons went straight through. After we've done that, after we tinkered and got those two things set, then we turned off the electric field and we watch as the electron goes through a path that would have had a radius of 0.325 meters. Using all this information, what's the charge to mass ratio of the electron? So the first thing I would have to do is calculate the velocity of the electron using the velocity selector formula. I just stick in the numbers that we were just given. Once I've got those numbers in, I calculate it, and I find that it's going just a bit over 10% the speed of light, which is pretty fast. 3.20-ish times 10 to the 7 meters per second. Okay, I've got that velocity. Then I can do the charge to mass ratio thing where I set up Fm equals Fc. And I do the whole thing where I make the two sides equal to each other, cancel the V's, and then solve for Q over M. And I plug in my numbers. I know the velocity, and I know the magnetic field, and I know the radius of the path. I do all that, and I get an experimental value for the charge to mass ratio of what we now today know are electrons. Now, a couple of things to point out. First of all, this two-step problem, makes a lovely double numerical response question because you have two physics principles. In the first part, back here, we're really doing that where we had said that the magnetic force and the electric force were equal but opposite, canceling each other out. F net equals 0, uniform motion. So that's the first physics principle that we used. And then here, heck, we're doing circular motion. So that means we're doing the whole F net is radially inward thing. So that's our second physics principle that we're using here. The other thing that I'd mention to you is, looking at that number, it's not exactly the right number. Because remember, this is based on experimental data, so we don't expect it to be perfect. Could I actually figure out the charge to mass ratio of an actual electron? Yeah, I've got numbers on a data sheet. I know the charge of an electron is 1.60 times 10 to the negative 19, and I know its mass is 9.11 times 10 to the negative 31. So I could actually just take those two numbers and divide them, and I get a number that's pretty close to that. You know what we should do? Is actually check it then. Because we have our measured value, the 1.70 times 10 to the 11 there, that's from the question that we just did. And the 1.76 times 10 to the 11 is the accepted value I get for Q divided by M if I use the values of an electron from the data sheet. And I can do that for protons or alpha particles or whatever I want also. But here, J.J. Thomson, cathode ray tube experiment, we're whizzing around the electrons. So I'd go through this calculation and I would find out that I was only under by about 3.13%. Good for us, good experimental results. So what does J.J. Thomson get out of all of this? His plum pudding model, which it was actually a friend of his that gave it that nickname, because when he described what it looked like, he thought, oh, it's a plum pudding, which is just a British dessert. It's basically cake with little bits of plum floating in it, okay? But somebody in the US, like in the 1990s, said, ooh, it's too hard to explain what a plum pudding is. So they said raisin bun? Honestly, when's the last time you asked for a raisin bun? Sure, it's a bun with raisins. How about chocolate chip cookie model or blueberry muffin model? I'd take any of those names over raisin bun. Anyways, whatever. What J.J. Thomson comes to a conclusion about is that number, about 1.76 times 10 to the 11, coulombs per kilogram. That many coulombs per kilogram? Well, that must mean that the electrons are incredibly small, because if they had any sort of noticeable mass, the charge would be gigantic. And we know that it's difficult to get charges to be gigantic. They just don't work that way. So he figures the electrons are incredibly small. And today we know that, at least as far as individual subatomic particles go that we have done active measurements of, they're like the smallest thing there is. So he basically says, I think what I'm seeing in this cathode ray tube then is all these little negative charges, which are independent little units, and they can be flicked out. And that's what we're doing in the cathode ray tube. And that's why we're seeing these negative charges flying across. But atoms are neutral. So there's got to be something to cancel out all those negative charges. And he basically says, yep, there is. The main sort of body of the atom is this thinly spread out positive goo. And because it's this goo that's kind of spread out, it never really moves anywhere. It's just sitting there with the negative charges floating in it. Now you can see why plum pudding, raisin bun, chocolate chip cookie, any of those sorts of names kind of apply to this. The reason that he figured he was never seeing the positive charges whizzing around is because it was that positive goo that was just sitting there. It was too much of a lump, but it is spread out kind of thin. I often use the example of I've given you too little margarine to spread on a piece of bread that's too big, so it's spread out really thin, but it's still enough positive charge to cancel out those negative charges. This is the model that he figures is what's going on. Now, this model sticks around for a few years, but what we're going to see is there's another experiment, somebody else's experiment, that kind of throws this one into the trash heap. Not that it's worthless or something, but it means that we have to evolve to something better. A few questions for you to look at. I hope this has helped you. Good luck.